A street lighting illumination design is to be performed in such a manner that the flux from the lantern is uniformly spread on the road surface and its surrounding, so that any obstacle or obstruction can be detected in time and necessary action can be taken. To spread the illumination uniformly, it is necessary to have photometric design of lantern to be good, as shown in this figure. The bad illumination can give patchy appearance of the street lantern when mounted. Illumination requirement of different class of road are given in this table with a uniformity of aerial as well as linear. There are two important factors which are needed by designers. Number one, the width of road, and the second is the quality of road surface. The width of road is more important factor which requires for design. Another important decision to be taken by a designer is the choice of rating of lantern and the light source. We decide the lumen output of the lantern. Lumen output directly relate to the mounting height of lantern. This is due to the limiting glare quality. For example, 5-meter mounting height is suitable for up to 3000 lumen output, whereas 5-meter to 8-meter mounting height is suitable for 3000 to 10,000 lumen, and 8 to 10 meters mounting height is suitable for 10,000 to 30,000 lumens, and 10 meter to 12 meter mounting height is suitable for 30,000 to 60,000 lumens. Mounting height and spacings are related to one another by lantern design. Thus, if lantern is non-cutoff types, then the spacing can be more than or equal to 4 times the mounting height. And if the lantern is semi-cutoff type, then the spacing is greater than or equal to 3 times the mounting height. But if the lantern is cutoff type, then the spacing is more than or equal to 2.5 times the mounting height. These figures are directly taken as basis. A street lantern system consists of lantern, the mounting bracket, and the pole. The mounting height from the light center of the lantern to the surface of the road vertical distance, whereas the spacing is the road length from center of pole to the center of pole of consecutive poles, either on one side or on opposite side. Arrangement of poles. Angle of tilt is the angle made by light center to the horizontal from the pole top center. And overhang is the length of the bracket between top center and the mounting point of the lantern. Rule for deciding tilt. Angle of tilt in degree is 0 for width being less than mounting height, and it is 5 degree for width equals to mounting height. But if the mounting height is 1.5 times the width, then the tilt can be taken as 10 degree. And if the width is more than or equal to 2 mounting height, then the angle of tilt can be 15 degrees. Now never more than 15 degrees shall be the rule to hold the angle of tilt. Whereas rule for deciding overhang. Overhang is always 10% of total width of the road, subjected to a maximum of 2 meters. The coefficient of utilization is the fraction of total amount of flux falling on the one section of the spacing from each lantern. This relates to the house side ratio of road width as road side and house side width of the street to house side ratio of a street. There are two curves, one for house side and the other for road side. Both of these values shall be added together to get the COU. Effective number of lantern in one section of spacing. In this figure, you see the two half lantern contributing to the spacing section. So in this case, only one lantern is contributing to the spacing section. Now the equation for calculating the spacing is given with the following equation. SP equals N into LLO into MF into CO divided by lux divided by W width. Equation number 1, where SP is spacing between consecutive lantern section in meters and is the effective numbers of lantern in one spacing section. LLO is lantern lumen output. MF is maintenance factor. CO is coefficient of utilization, and lux is the maintained illumination achieved by such design. W is the width of a street in meters. In this analog design, total numbers of street lantern N for length of L meter street, N equals small n into L upon SP plus 1 into bracket equation to where N is total number of lantern on the road. Analog design continue. The value of N is 1 for single-sided staggered pole arrangement as shown in this figure below. N, that is effective number of lantern, is true for opposite-sided or central isopole arrangement as shown in the following figure. And n equals 4 for opposite-sided and central isopole arrangement. Example 1. A 1 kilometer road having 10 meter width is to be lighted for 15 lux maintained light level. Decide spacing for 12,000 lumen street lantern and calculate total number of poles. Lumen output of lantern is already given. So referring to the slide 4, mounting height of the pole is 10 meter. Using cutoff lantern, we decide one side arrangement maintenance factor is taken as 0.64. COU for street side ratio is 1. House side ratio is 0.1. Referring to the COU curve, COU 0.45 plus 0.030 equals 0.48. Analogue design, example 1 continue. Spacing and effective number of lantern lumen output, maintenance factors, COU, lux, and width shall be kept in the equation, and we get 25 meter spacing. This spacing shall be used in second equation, which gives total number of lantern for 1 kilometer length. We get 41 numbers of lantern for 1 kilometer of length, one-sided. Analogue design, example 2. Design a street lighting system for 1 kilometer long and 30 meter wide road. Maintained lighting level shall be 30 lux. Select 12,000 lumen lantern. Pole mounting height comes to 10 meter. Using cutoff lantern, opposite plus central reserve arrangement. In the following figure, we get 4 lantern effective per spacing. Putting all these values into the equation as given for SP spacing, we find the spacing comes to 20 meters. Now to find the total number of lantern, the equation shall be used, and this 20 meter spacing shall be used to find out the total number of lantern by this equation. We find as 204 numbers per kilometer lantern.